There's another variable that's often talked about when we discuss gases, and that is the density of a gas. So how do we relate density and the ideal gas equation? So here I'm just showing a picture from World War I, where there was a lot of poison gas that was released. You can see it hugs the ground because of its high density of that gas, and so soldiers had to walk through it, and thus the gas masks, etc. So how do we relate density and the ideal gas law? Well, might help to just start by reminding ourselves of what density is. So density is mass divided by the volume of the material. Now, how do we relate this to the ideal gas law? Because we don't have mass in the ideal gas law. And it's true, we don't. But if we take the ideal gas law and we rearrange it here to solve for number of moles over volume, we have N over V is equal to P over RT. Now, if you take the number of moles and you multiply it by the molar mass, you would get mass. So if we take this rearranged ideal gas equation and we multiply both sides by the molar mass, remember you can do anything to one side of an equation, providing you also do it to the other side of the equation. So if we multiply both sides by the molar mass, symbolized here with this fancy M, then you would get the number of moles times the molar mass. So this now becomes just mass. And so then we have mass over volume. So this whole quantity then is just density. And so I can get from this that the density of a gas is equal to the pressure times the molar mass divided by the ideal gas constant times temperature. So what we get out of this is that density of a gas depends only on the pressure, the temperature, and the molar mass. And we can see some direct relationships. We can see that density is directly proportional to the pressure and directly proportional to the molar mass, but inversely proportional to the temperature. So as the pressure increases, so does the density. And if we have two gases, one that has a lower molar mass than the other, and all the other conditions are kept the same, then we'll see that the density of the gas with the higher molar mass will be higher. Temperature, this also explains several things. So it's inversely proportional. So when the temperature is high, the density is less. And we can see that for, this is why hot air rises. Hot air is less dense, and so it rises because it's displaced by more dense air that sits at the bottom. So let's go through an example of this. What's the density of propane at 769.2 torr and 56 degrees Celsius? So I'm given the pressure, I'm given a temperature, and I'm not given the molar mass, but I am given the chemical formula, so I can determine the molar mass simply by summing the atomic weights. So I know pressure, temperature, and molar mass, so I can solve for the density. First, have to decide which gas constant to use, and here my pressure unit is in torr, so I'm going to use the value for R that has torr in it. And I will need to convert my temperature to a Kelvin here, to absolute temperature, and then sum up the atomic weights to 3 times 12.01 plus 8 times 1.01, and I come out with 44.11 grams per mole for my molar mass. And then I simply substitute all of these values in. And what I'll notice, if I keep careful track of my units, is now Kelvin will cancel, moles will cancel, torr will cancel, and I will simply be left with a density in grams per liter. Now, it's very important that we keep track of our units here. The density that falls out of this has units of grams per liter. Now, we're more familiar with density in terms of grams per milliliter or grams per centimeter cubed. So we may want to convert this value from grams per liter to grams per milliliter. So I can do that simply by converting the liters to milliliters. And I come out with a density for propane of 0.00165 grams per milliliter. Now, what about another example here? Let's say that I knew the density of a gas because I could measure that. I can measure the mass of the gas, and I could measure its volume at a particular temperature and pressure. What if I wanted to calculate the molar mass for some gas? Maybe I didn't know the identity of the gas, but I was able to make those physical measurements. Well, I can do that fairly simply as well using the equation. So I know the density, I know the temperature, and I know the pressure. So I simply rearrange to solve for the molar mass and get molar mass is equal to the density times the gas constant times temperature divided by pressure. And then I substitute those values in after converting temperature to its Kelvin, and using the appropriate gas constant here because of my units of pressure and torr. And then I substitute those values in, and I'll come out with a molar mass of 171 grams per mole. And the last question here might be, why do I refer to this as being a vapor rather than being a gas? Well, it is in the gas phase, but remember back to the very beginning here in chapter 10, where we mentioned that most gases, molecular gases, at room temperature have low molar masses, less than 100. And what we would see instead is if we have a material that, if we talk about the gas phase of a material that's normally a liquid or a solid at room temperature, then we refer to it as a vapor. So this gas here has a molar mass of 171. That's greater than 100. So most likely this is this material is normally a liquid or a solid at normal room temperature and pressure. And this might be just the little bit of vapor that kind of collects above that liquid.